Everybody, welcome back to Biostat. Today we're going to do lecture 3 over discrete random variables. We're going to talk about those in general and basically what a random variable is in general. And we're also going to specifically talk about the binomial and the Poisson distributions, which are two types of discrete distributions. These are two that are probably predominantly that are used fairly often in biology, so these are good to utilize and show you guys about, especially you biologists in the group. So let's get going. So we'll go over some of the basics first, and then we'll talk about, as I said, the binomial and the Poisson distribution. So let's get on to it. So what is a random variable? Well, it's what they call a real valued function, and a real valued function is just a function that finds the probability of specific numerical values. Like our data, in other words, would be real valued. In other words, they'd have value numbers to them associated with them. And these are defined over an entire sample space. So the function will give us the layout of the entire of the probabilities over the entire sample space. All right. These can also be thought of as a variable whose value is determined by the outcome of a random experiment. Random experiment, real quick. That's any experiment you might do. Like, in other words, collection of data is considered an experiment. When you collect data, you're usually performing some kind of experiment in the real world. It could be like you're collecting information on patients with certain diseases at a hospital or something like that, but you can't just go and grab the first 50 patients off the list you see, because that's not a good representation of your population of all people with this particular disease. Therefore, you have to randomly pull people from this, and we'll talk a little bit about sampling at the end of lecture 4, and you'll kind of see where the randomness comes in when you do experiments there a little bit. We won't get too into detail on that in this course. That's really more for a research design course, but we'll talk about it from here here and there. But randomness is important. Random variables can either be continuous or they can be discrete. We will talk mainly about discrete today, but we'll mention a little bit about continuous today and talk more about it in lecture 4. Some things about notation. Let me go ahead and get both these bullets up. So we'll usually use an uppercase letter such as Y to denote a random variable. Basically, the capital letter Y is used to define, make a worded definition, if you will, of what the random variable is. All right. And we use a lowercase letter such as little y to denote the particular value that a random variable may assume. In other words, the actual value. All right, so that's the key word with lowercase y, is that it's a value. Uppercase Y is a denotation or a definition, if you will. Okay, and usually we'll write things up like, you'll see me do this occasionally. The probability that y equals little y is saying that the random variable takes on the value of little y. So this right here would be an actual number. Okay. But that's the notation for the probability that y takes on that y value. Sometimes in shorthand we'll write little p of little y, but this is specifically for if you equal a value. In other words, if you equal that exact value. So say you're interested in seeing what's the probability that maybe the random variable was the number of patients, or you get collected data on the patients with a specific disease, and you wanted to know how many of them listed were terminal, and you could say what's the probability that y equals 20. Then you could find that probability that exactly 20 of them had that terminal disease. That's just a for example there. But sometimes we're often interested in several probabilities of several random variable values that are defined in our sample space. Okay, and the notation is not much different from this right here. It just uses inequalities instead, so we could look for the probability that y was less than little y. In other words, what we would be doing would be adding from whatever value we put in for little y all the way down to so that random variable that represents little y. We'd be looking for the probabilities of that value, the values, and the values below them. Similarly, you could go greater than, and you'd be looking for anything greater than that value. And I should reiterate, the first one, it's every value below the value you put in, because this is strictly less than and strictly greater than. But if we wanted the probability of the value less than or equal to a specific given value, then we would include this value in our calculation. We'd include the probability of whatever that value is all the way down. And similarly, if we do it greater than or equal to, we're looking for that value of y all the way up to the biggest random variable we have in our sample space. Sometimes we might also be interested in finding the combined probabilities, or the added up probabilities, between several values in a range, or like an interval. So maybe we'll I'll just for sake call the lower bound y1. Maybe be interested in finding that all the way up to y2, so we get a little compound inequality. We're looking for the lower bound and the upper bound, and we're adding everything from those endpoints in between. Okay, so occasionally we might be looking for that. A little word here on continuous random variables. When observations on a quantitative random variable can assume any one of an uncountable number of values. Uncountable means that essentially means decimal numbers, because usually we round decimal numbers off, and so we consider them uncountable because they're not something that if we rounded them off, we don't know exactly what the value was, and so and they can take on any number in a line interval. Then the variable is called continuous. Anything that is continuous is, as I think I've stated before, is something usually that's measured. All right, most continuous variables are some kind of measurement. These can include examples such as the weight of a surgical glove, which in this case the weight being a measurement, because the weight can take on any small interval, a value in a small interval of weights. Here I've got a random variable titled z equals the total annual rainfall at a location, and this can contain values such as 0, 3.15, so forth and so on. The word annual makes me think it's an average rainfall for the year in a location, and averages typically are measurements too. They're measurements of center. So we'll explore more about continuous random variables in Lecture 4, and we'll deal with these quite often in the class, but more on these later. All right, so discrete random variables. A discrete, basically a discrete random variable can only, these are values or numbers essentially that can only assume a finite or countably infinite number of distinct values. The word distinct is important there. Most people gloss over that, but what distinct really means is implies the numbers have to be a whole number. In other words, they have to be exactly 0, 1, 2, 3, 4, so forth and so on. They have to take on distinct values. So our random variables will be represented by those kind of numbers. Examples in this can include the sum of the faces of two fair die. So if you roll two die and you sum them up, you get the possible sums of 2 through 12. All right. We're going to do an experiment with that here shortly. And we've got another random variable defined as x equals the number of pinholes in a surgical glove. And those numbers can take on in the sample space here, which is what you're seeing. These are the sample spaces. Here and here for each one of those. Can take on any number from 0 all the way to as many pinholes as we can count in those gloves. Okay. Thing to note here real quick before we move on is that capital Y equals the sum of the faces of two fair die. Notice the capital Y here is the definition again of the random variable, but the actual value of the random variable is what's listed in the sample space here. So that's the lowercase y. Here in this case, I'm going to use the lowercase x because I used a different variable name there, which is okay. The variable names are kind of arbitrary, I'll probably use Y because I'm stuck on that at the moment, but occasionally I might pop an X in there here or there. The first theorem we have here pertains predominantly to probability. For any discrete probability distribution, or really any probability distribution, doesn't matter whether it's discrete or not, the following has to be true. Any probability you calculate, that's what we're calling P of Y here in the center, has to fall between 0 and 1, but it can include 0 and 1, because you can have a 0 probability. In other words, that particular event doesn't happen. Or you can have a probability of 1, which means that probably definitely will happen. Those two probabilities are rare in science. You might get close to 0, but you very rarely get exactly 0. And also, since all of these probabilities have to be values between 0 and 1, we also have the second bullet here that says that if you sum all the probabilities together from the sample space, they should sum up to 1. They should add up to 1. For example, in the sum of the faces of two die, if I found all the probabilities for each one of these random variables in here and added them together, we better get 1. One other thing to note about bullet 1 is that if you ever get a probability that is bigger than 1 or is negative, you did something wrong. That is a clear-cut indication. I try to teach people that, and it seems like some folks don't get that. But if you get a probability that's greater than 1 or negative, you need to double-check your calculations or how you entered your stuff into R, because you're definitely wrong, and you want to correct that. All right. Should you never get a probability bigger than 1 or smaller than 0. So let's take a look at what a probability distribution is. A probability distribution for a discrete random variable is all of its possible random values together with their probabilities. All right, so it's basically a table or sometimes a bar plot or histogram of all their probabilities listed out together. And so in example 1 here is a good quick example of, so the following probability distribution for a random variable defined by Y, capital Y, equals the number of children that are girls in a 3-child household. All right, and we see the random variable across the top here, Y, can take on 0 for 0 girls, 1 for exactly 1 of the 3 children is a girl, 2 of the 3 children is a girl, or 3 of the 3 children, or all 3 children are girls. Okay, so we've got that there, and then below we have the probabilities listed out. That's 0.125, 0.375, 0.375, and 0.125. And don't worry, I'm not going to have you guys do a lot of this kind of thing in this course. So if you weren't strong with probability to begin with, I won't make you do things like this in this class. But I just want to kind of go over what these things are. So that being said, how did I get these values? Well, if I just use the old, what I call enumerate a list of possible outcomes for these situations, and I think, okay, if I have 3 kids and each one can either be a boy or a girl, I have the following outcomes that I could list. I could have boy, boy, boy. That's the no girls. To have 1 girl, go ahead and put a G there with 2 B's. 1 girl, 2 boys. And I can shift that girl around and go boy, girl, boy, 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 girl. Thinking about the order they're in as they go from left to right somewhat matters here, because the children are different children. So there's 3 different possibilities there. Notice that. I could have 2 girls and 1 boy, and I can shift the boy around to kind of give myself other variations here. And I have girl, boy, girl, and I have boy, girl, girl. And notice there's 3 ways that can happen when I just shift the boy around. And lastly, the one I'm missing is, well, what if they're all girls? There's only one way that happens. Boom. And so what you're seeing here is, since there's 8 total different possibilities of sex assigned to 3 children in a 3-child family, and so since there's one instance where there's no girls, all boys, This is 1 out of 8, which is 1.125. Since there's 3 instances here of where there's only one girl, that's 3 out of 8, which turns out to be that. So you can kind of see where I'm going now. There's 3 instances here where I have 2 girls and 1 boy, 3 out of 8. And then finally, only one where I have all girls, 1 out of 8, and that's equivalent to 0.125. So that's where those numbers come from. We'll find out later that this actually fits our binomial distribution as well. All right. So let's do an actual example from scratch. With that example I mentioned earlier, the sum of the faces of 2 fair die. And we'll kind of play around in R a little bit with this too. So quite simply here, we need to know what the possible values of are for the sum of the faces of 2 fair die. We also need to know how many outcomes we're going to have so we can figure out the probabilities that we have at our disposal. When you roll 2 fair die, they're 6-sided die. When they say fair die, we're usually talking about, most of the time if they don't mention it, we're talking about 6-sided die. If you roll 2 of these guys, each one has 6 sides. So there's 6 possibilities on one of what can come up when you roll the first die, and 6 that come up when you roll the second die. So if you multiply those together using something we call the multiplication principle, and this only works with if your die are 2 different die, or you're rolling a die multiple times. In other words, that each roll is independent of the next. The number of outcomes we should have in our sample space is going to be equal to 6 times 6, which equals 36. So there's 36 possible pairings of the faces of the die that come up when we roll them, and we can sum them together. So there should be 36 different sums. All right. That doesn't help us with our table yet, but we'll keep that 36 in mind as we do what we're about to do next. So I made a little table here because it's easier to visualize these things this way. And across the column headers, I have die 1's faces 1 through 6, and down the rows I have die 2's faces 1 through 6 listed. So we just need to come up with all the sums that we'll see here, and this will give us 36 because it's a 6x6 box in here that I have blank. And so if I add 1 and 1 together, I get 2. 1 and 2 together, I get 3. And I'm just adding the row with the column headers for each row. 2, 3, and I should get 4. So I'm just adding 1 to each of the columns right now. 5, 6, 7. And this starts to get like patterned in a minute. So now I move down to the second row and I say 2 plus 1 gives me 3. 2 plus 2 gives me 4. 2 plus 3 gives me 5. 2 plus 4, 6. And I start seeing I'm just going up 7, 8. And then 3 plus 1 is 4. 3 plus 2 is 5, 6, 7, 8, 9. And you can start seeing pattern. The next one's going to be 4 plus 1, which is 5. And then I get 6, 7, 8, 9, 10. These are all my sums. 5 plus 1 is 6, 7, 8, 9, 10, 11. 6 plus 1 is 7, 8, 9, 10, 11, and 12. So we can see both all the sums that we have and all the ways we could get those sums. All right. I'm not so much concerned about the ways we get them, but how many of the sums we have. So if I look here, I've got 1, 2, pair of 3s, sums of 3, 4, 3 4s, 3 sums of 5, 5 sums of 6, 6 sums of 7, 5 sums of 8, 4 of 9, 3 of 10, 2 of 11, and 1 of 12. So what am I going to do with those? I'm going to use those values that I get and put them in up here for y. And so I get the sum 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Those are all my possible random variable values that I would need to find probabilities for. So little p of y, plug it in there real quick. I'm going to count how many of these sums I have and divide them by 36. So by hand, it's nicer to leave these things as fractions. So I only have one sum of 2. so that's 1 out of 36. I have 2 sums of 3 down in my table, so that's 2 out of 36. 3 sums of 4 out of 36. 4 sums of 5 out of 36. You can kind of see where I'm going. 5 sums of 6 by 36. We got 6 sums of 7 out of our 36. 5 of the sum of 8 of the 30s. Let me write that correctly here. 5 out of 36. And it goes down. There's 4 sums of 9, 3 sums of 10, 2 sums of 11, and finally 1 of 12. All right, so there are our probabilities. So if we're building this table, that's what we would do. Let's play around with this in R real quick so we can see that we can get these values pretty quickly in R by building a couple of vectors and dealing with that. So let's switch over to R real quick. So in R, I'm going to create a vector called A, just because I don't have a better name for it. And I'm going to create the vector of the counts that I saw in the box over here, the 1, the 2, the count, the number of times I saw each sum, 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1. I want to create that. So quickly, the way I can do that is go, I need the numbers 1 through 6 listed in that order, comma, and then I need to go back down from that 5 back down to 1. So I can do it using that colon feature in here to do it quickly without having to list them all individually. And there we go. We've got the numbers 1, 2, 3, 4, 5, 6. If I do A, and then 5, 4, 3, 2, 1. Now I want to create a vector called probabilities, P, equals, and I'm just going to take the vector A and divide it by 36. And we'll get the actual proportions here in this case. And there they are. Now they're rounded out to quite a number of decimal places. You could change that if you wanted. Not necessary here. But 3 or 4 decimal places is usually good enough for most probability values to be given to someone else. Let's check and make sure that we've got a valid distribution here. So I can use the sum command, and let's sum the values from P, all the probabilities. If they add to 1, then we're good, and they do. So there's that rule that we said they all have to sum to 1, and all the values in that samples, in those probabilities for our sample space are all between numbers that are between 0 and 1. Okay. I think that's really all I wanted to mention to you about that. Again, I'm not going to be making you do a lot of this kind of thing in this course, but I just might want to kind of have a refresher over probability in general here. Okay. If you wanted to round those probability values, you could say round and then open a parenthesis and put P, comma, say round to 3 decimal places if you wanted, and it will give you that out rounded to 3 decimal places. You could do things like that for output purposes. And that's all we're going to say about that. We're going to move on. So here's the probability histogram, aka really a bar plot here, but it acts like kind of like a histogram in this case. But we see that the data is pretty normal here, and as we'll see here in a minute when we talk about how you find the mean and stuff, it's a nice bell-shaped curve. The highest bar here is a 7. At 7, it's got the highest probability. This will turn out to be the average of this data set because it's so symmetrical. I mean, everything just falls off perfectly in both directions. It's a nice bell-shaped curve. And when it's a perfect bell-shaped curve like this one is, the mean is always dead center. Not always the case when you deal with some other distributions, but when it's perfectly normal, this happens. Okay. So some more about discrete random variables in general. These formulas here are the formulas that if you have that sample distribution, that distribution table like we looked at here a minute ago, this is how you would calculate the mean, the variance, and the standard deviations of these things. I'm going to do the mean in R for you real quick just to show you. So right here, if we're looking at the formula, you've got the summation, that's what sigma stands for, this thing right here, of each of the values for y, in other words the 2 through 12 in our die problem, and you multiply each one of those by the probabilities associated with each one, and then you will sum those together, and that should give us the value of 7. So going back to R, since we already have that in here real quickly, if I wanted to calculate the mean here, I need to create a vector of values for y, because I don't have my y values in here right now. And really all I need is the numbers 2 through 12, so I don't even need the C function here. And I have that. So now to find the mean, I could literally just go, okay, I could call it a variable name, maybe say m for mean, and then say y times p, which is the probabilities. And actually what I want to do before I do that is I want to sum those up, because I want the sum of those, and that matches the formula that we see on the slide. And hit enter, m should give us 7, and it does. Okay. I'll refrain from doing these other two in here just to save us some time. Again, I'm not going to make you have to use these particular formulas. You'll have other formulas you'll use for specific distributions that are a little simpler. The variance here is similar. You take each of the values 2 through 12 and square them, then multiply them times the probabilities, add those things together, and then subtract the mean we just found squared, and that would give us the value of 5.833 repeating. And the standard deviation is just the square root of the value, that value there, and that's all there is to it. Okay, but if you don't know what your distribution is, these are the formulas you would have to use, and you'd have to list out your sample distributions in a table like we saw. Fortunately for us, the distributions we're dealing with have nicer formulas than this. All right, and don't require as much work. So let's go ahead and get into the binomial probability distribution. All right. So some experiments consist of a sequence of what we call identical and independent trials. All right. Each of which only has 2 possible outcomes, hence the name binomial. Either you fit the description we're looking for, or you don't. All right. So some examples of this might be the number of cases of chronic bronchitis in the first year of life, the number of cells that will be neutrophils or not, and the number of children that will be male or female, like we saw with the very first example. So the number of cases of bronchitis, chronic bronchitis, we'll actually do an example with that here shortly. But either you get it there in the first year of your life or you don't. All right, so that's what we're going to be looking at there. You can either be a neutrophil or you won't. There's that binomial situation. You're either going to be sex at birth is either going to be male or female. Simple as that. All right, so you got the quality or you don't. And so we call all these binomial experiments because of that. Specifically, in this definition here, we're going to talk about the properties of the binomial distribution. So the properties here. So these are important. I would definitely know these because these are definitely quizable material. But the first property here says the experiment consists of a fixed number of identical trials. All right, which we notate as little n. Okay. So we have a fixed number of trials. Each trial results in 2 outcomes, either a success or a failure. Successes are what we're interested in. They don't have to be good things. I mean, they can be, some horrible things, but nonetheless, they're what we're interested in finding out about. The failure is just the opposite thing. All right, is the other end of the spectrum. The success is the thing you want to know, or the quality you want your experiment to have, and the failure is the opposite of that they don't have that thing. I don't know why they use the word success and failure in these stats textbooks. It's always bothered me. But nonetheless, that's how they word them. The probability of success on a single trial is always going to be equal to the value, what we call P. And it remains the same from trial to trial. So no matter how many trials you have, in other words, what a trial represents is like that you get 0 things with the success that you're looking for, that you get 1 is another trial, 2 be another trial. Like you have 10 items maybe you're looking at and you're like wondering, out of those 10, how many successes do I have? Well, the probability of success of having however many successes you have on any one of those things is going to remain the same from trial to trial. Also, the probability of a failure is also going to stay the same from trial to trial, but it's notated as Q in most texts, or sometimes they'll write it as 1 minus P because it's the complement of P, of the success. So if you know the probability of success, you actually know the probability of the failure just by taking 1 and subtracting that P value from it. The trials are independent, and we haven't talked about independence much yet. But independent, for 2 events to be independent, they can't have, in other words, when 2 events happen, they can't happen to where they can't affect one another's outcomes, the fact that they will happen. So, for example, a good example of independent events will be the sex of the children. If you have 3 or more kids, the sex of the first child born and the sex of the second child born have nothing to do with one another, because there's so many elements that go into being involved in making and that process happen, or the outcome happen. But the first child has no effect on whether the second child is male or female, so they're independent. The rolling of the die is considered independent because rolling of one die doesn't affect the outcome on that die, doesn't affect what the second die rolled comes out to be. So that's really what independence is. It's really independent events are events where the first each event doesn't affect the others, the outcomes of the others. All right. And the last thing here is this: is the random variable of interest is capital Y, and it's just saying, this is basically saying that capital Y defines the number of successes observed during the N trials. So that's what will be of our interest when we're talking about binomials, the number of successes we see. Here's the probability distribution function for the binomial distribution. It's not a bad formula. Some of you may have seen this before. I'm not going to get into this big time here because we're not going to utilize it by formula. We're going to let the R functions do the work for us. Okay. So the probability distribution function PDF for binomial random variable Y based on N trials with a success probability P is calculated using this formula right here. You notice they've got a little P here and a little Q. Those are our success and failures, and they've both got exponents associated with them. That Y value here represents the number of successes, or the number of successes we want to find. And so the number of successes is raised to that value. And the number of failures is raised to that value minus the total number of trials we have. N minus Y will give us the number of failures. This first thing up here, I don't want to go into too much detail in this course because it's kind of beyond the scope of our class. But if you've had binomial theorem or binomial distribution in other classes before, you know what this means. This is basically saying the following. It's a shorthand for N choose Y. It's saying if I have N trials in this case, how many combinations do I have? It's called a combinations formula. How many combinations do I have of Y successes? So out of N trials, how many cases I have? Think about the boy, girl, boy thing real quick. When we had 0 girls, there were all 3 boys. So this, for that particular example, if we said 3 choose 0 of them to be girls, we saw that there was only one outcome where there were boys, and so this function actually counts that for us and adds that into the formula, so we consider that that's how many times that occurred. When we did the 1 girl, there were 3 outcomes, and so this formula here would say, well, what's 3 choose 1 item to be a girl in this group? So 3 with 1 success, and we saw that we had one girl in 3 different combinations in there, so this would come out to be 3. That's all I'm going to say about that. We'll leave it alone at that, and we'll talk about the R functions specifically now. The R functions have this in them, and so there's two variations for discrete variables that you occasionally have to use. The PDF function gives you exact values. So if I use that formula and I plug say a 4 into the formula we looked at above, I'm going to find out the probability of getting exactly 4 successes. To get that in R, we use what we call the D binom function. It uses exact. So if you want to know exactly a certain number of successes, you use this guy. If you want to add several events together, in other words, maybe 0 through 10 successes all together, you're going to use the P binom function down here. This was what we call the cumulative distribution function because it adds several values together. And as a matter of fact, it follows this rule right here. It says the probability that y is less than or equal to whatever we plug into it. It's going to add every probability from 0 up to that number that we plug in. So every random variable we plug in, every random variable from 0 up to where we tell it to stop, it's going to add all those probabilities together for us. Okay? And so the inputs are really similar for both of these guys. You've got y, n, and p. So it takes y, which is the value either you want to know the exact value of, the probability of, or the value that you wanted to add probabilities up and stop at in the p binom version. N and p are the same in both cases. N is the number of trials you have, p is the probability of your success. After that, R knows what to do with it. Okay. I'm going to go a little bit more about p binom here in just a second because I think it's important. But before we do that, let's talk about the binomial distribution and what really affects the change in how the distribution is laid out. In other words, what structures its shape. So I'm going to talk mainly about this first row here, but here I chose my number of trials to be 5 for all 3 of these graphs. And all I changed was the probability of success in each one. And I went from 0.2 up to 0.6. Notice what happens to the graph, or the bars in the graph, and how they shift based on that probability. So this smaller probability here of 0.2, we get what we call a right skewed distribution. These are good terms to know when you're defining, when you're trying to describe either histograms or bar plots to me in projects. This looks right skewed, and it is because this longer tail is on the right and the higher bars are on the left. The one in the middle is shifted a little bit. It's got a little less of a longer tail on the left hand side, but nonetheless it's still slightly skewed, but I would call this approximately normal. And then the one with 0.6 as its probability of success is skewed the other direction. It's got its longer tail. It's got more of a tail on the left hand side, so we call this left skewed. Okay. And the graphs below kind of follow the same kind of pattern here, except for one thing I did give you was I gave you one where the probability of success was exactly 0.5, and whenever that's true, the probability of success is 0.5, you end up getting a perfectly symmetrical normal. I would call this a normal bell-shaped curve distribution. Okay. So let's talk, I don't have this slide in this next one, I'm just using a blank page here, but let's talk a little bit more about the p binom function. I know this might make us go over a little bit, but I'd rather do this than not. Alright, remember p binom, as I stated before, takes the 3 arguments in, y, n, and p. There's an additional argument that we can throw into this, and I'll show that in a moment. But what this does is, let's say, for example, you were wanting to find the probability of some value being, or finding the probability of being less than, say, 5 where p equals 2 and n equals 12. Okay. So less than 5 is the key here. So if you think about a number line, or you list out your discrete random values 0 through 12, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and you were to plug in less than 5, you want to know the probability that you're wanting p binom to add up for you is going to be these 4 numbers here. Okay. Now remember, y takes on the value that you want it to stop at. So if we want less than 5, we have to plug in a 4 for this. So in R, we would plug in p binom 4 comma, in this case, the n is 12, and then 0.2 for the probability of success, and it would spit out that answer for us. Okay. If this had said less than or equal to 5, or at most 5, then we would have plugged the 5 in there, because we would want to include that 5 in there. So you have to keep abreast of what you plug in based off of what you're trying to find, because y will add up to where you tell it to stop. Now, there is an alternative version of this, which is called p binom. It's still the same function, but it has an additional argument that we're going to throw in there called lower dot tail equals. And this is usually set equal to true, and what that little thing is telling it is you don't have to put this in usually. If you don't put it in like we did up here, it adds from 0 up to where you tell it to stop. But if you put lower dot tail equals false in there, it's going to add the other direction. In other words, instead of going from the number you put in down, it's going to put in from the number you put in, it's going to go above the number you put in up. Let me show you what I mean. That's a little confusing at first, I know. Remember that on the other page I said this finds the probability that y is less than or equal to little y. This one here finds the probability that y is greater than little y. Alright, so it's a little bit different when you throw the lower dot tail equals false. So let's say I wanted to find the probability of at least 7 with the same thing. So where p is equal to 0.2 and n is equal to 12. Well, in this case, I'm still thinking of the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, all those discrete possible values. But if I want to know at least 7, that means 7 or more. So I really want to add these numbers here together. So what the lower dot tail equals false will allow me to do is do that. Alright, so there's 2 ways I can get this answer. I can either go p binom. Notice this right here. If I plug 7 in there, it's going to exclude the 7 because of that strictly greater than symbol. So whatever number I plug in there, it's going to add everything above the number I plug in. So I don't want to plug in this number here. I want to plug in this number here. I'm going to plug in just below the number I want. This only works this way, by the way, with discrete random variables. With continuous random variables, this kind of thing doesn't matter. But for now, I'd have to plug in 6, comma, 12, and 0.2, and then put that lower dot tail equals false in there. Alright, so that's one way you can get that. It's the way I've started using more often myself because I like that, but it doesn't really matter. There's another way to get this. I'm going to erase this real quick and show you the alternative way. So the alternative way that you could do this would be to consider the complement rule, where if you take the probability of the whole sample space, which is 1, and subtract the stuff you don't want to be in there, which is this stuff here. You don't want those probabilities, you want the ones I boxed in. You want the sum of those probabilities. Then you can just do p binom of again, we want to add all the way, we want to take away what we don't want, and the squiggly line's what I don't want, so where does the squiggly line stop? At 6 again. So it's the same kind of principle as the lower dot tail thing. 6, and then I enter 12 and 0.2, and that, if I put that into R just like that, it will give me the answer I want. Okay, we're going to do some examples where I do this, and I will do both versions each time. All right, so let's get to it so that we don't run out of time. So here we go. I got a sample of 1,500 families. That value is going to be my N. Okay. And we're going to use the fact, and these families are families where both parents have chronic bronchitis. We're going to use the fact that the incidence rate of chronic bronchitis in the first year of life is 0.05. So that's our p-value. That's our probability of success. Not quite successful. We don't want anybody to have that, but people get it. The probability of exactly 75 cases of chronic bronchitis is what we want to find first. So I'm going to do all this in R rather than writing it out. And these will be the R solutions will be in the R code only file that I've put in there too, so you can see them there. But let's just do these in R so I can save us some time from having to write things out. So the first thing I want to do is find exactly 75 cases. Let me clear out my stuff from earlier. And since it says exactly, I know this is a D binomial, so exact for D binom. And in that parentheses, I need to put the number 75 exactly, and then just the N value, which is 1,500, and 0.05 for P. So separating those by commas. If I go and hit enter, I get the value of 0.0472. So that's just a little slightly unusual to see 75 cases of chronic bronchitis. Okay. And that's pretty much all there is to the D binom. So you see the word exactly, remember to use the D binom. Probability of no more than 50 cases of chronic bronchitis. So the key words here are no more than 50. We need to look at that and think, okay, well, no more than 50 means 50 or less. No more than 50. So we want to go and add all the way from 0 up through 50 is what that's telling me. No more than 50, 50 or less. So in R here, I want to do D binom. Not D binom, sorry. We want to add up P binom. And in here, since I want to do 50 or less, I need to do 50, comma, the 1,500 and comma, and then 0.05. And then when I hit enter, I get a really small probability, so it'd be very unusual for us to see 50 or less cases of this stuff, of this disease, or not disease, but this sickness. The last one is one where we utilize that second thing I just talked about, where we can utilize that lower dot tail equals false if we want to, because it's asking us to find the probability of it that we get at least 75 cases of chronic bronchitis in the first year of life. So at least 75 means 75 or more. All right. And so in R, remember 75 or more here, we can do two different versions. We can do 1 minus the probabilities we don't care about. Since we care about finding the probabilities of seeing 75 or more cases, we don't care about the probabilities of finding 0 to 74. So we're going to let the p binom function find us the probability of that. So up to 74, because we don't want that value in there, we're going to take the whole 1 minus p binom 74, comma 1,500, comma 0.05. And there's a pretty high probability that we're going to see 75 or more cases in this instance. If you use the lower dot tail equals false, it's the same concept. You'd use p binom of 74. Again, remember with the lower dot tail equals false, what we're about to throw in there, we want to put the number just below the number we really want. So it's the same value we put in the other version a minute ago, and then 0.05, and then we just put in the lower dot tail equals false. and it gives us the same answer. So either way you want to do that is fine by me. I don't care. If one of those explanations made more sense to you than the other one, then by all means go with it. If you have more questions about that, then you can ask. I'm probably going to utilize this from here on out if we have to use it. All right, just to save us a little time. Okay, so that's how we answer a question like this. Let's do one more version here. Suppose a group of 100 women ages 60 to 64 received a new flu vaccine in 2004, and 5 of them died within the next year. Is this event unusual, or can this death be expected for people of this age sex group? In other words, we're asking really how likely it is that we see 5 of the 100 women, at least 5 of the 100 women who received the vaccine to die next year. So that at least 5 is kind of important to us here. The 5 is also important to us in the 100. Assume that the probability of death in the next year for women of this age sex group is 0.009. So there's our p-value. So our p is 0.009. Our n in this case is 100. And our y value is 5, but we want to know at least 5. That means 5 or more. So in R, remember, I'm going to use the lower dot tail equals false version. But remember, this is 0, 1, 2, 3, 4, 5, 6, ... all the way up to 100 trials. That's my listing of my discrete values all the way through all the trials. I'm interested in finding at least 5, so 5 or more. And I don't care about the stuff below it. So remember, if I use the lower dot tail equals false, it's going to add up the numbers above the number I input. So since I want 5, I'm going to have to input 4 as my first input here. Okay. So let's do that real quick, and then we'll talk about what the answer means. So if I use p binom, and I put in 4 as the number I want it to start afterwards, and then my n in this case is 100, and my p-value is 0.009, and then I throw in the lower dot tail equals false into it. I get a really small value. It's very unlikely that 5 or more women would have died in this particular instance from this vaccine. So that's the numerical answer that would support your verbal answer here, but your verbal answer should really be something more along the lines of, since the probability is so small, I mean, anything less than 0.05 is kind of considered unusual. I don't think I've mentioned that yet, but that's usually the cutoff for most people. Sometimes people want it to be a probability to be much smaller than that to be considered unusual. But since this probability is so small, we can conclude that it would be very unlikely that at least 5 of them would have died the next year after receiving this vaccine, and probably be grounds for halting the use of this vaccine. So that's the kind of explanation I want. You just telling me yes, it's unusual, or no, it's unusual with no explanation will get you no points even if you calculated the value right. This class is about about explaining your findings more so than it is about getting your findings. And so I'll be a very stickler about that in projects if you don't explain things to me. Especially being that this is a 3000 level course. So you've been warned. So let's move on from that and show you one other thing about the binomial distribution really quickly. Let y be a binomial random variable based on n trials and successes probability p. All right. Then the following formulas will give you your mean, your variance, and your standard deviation for this particular distribution. Matter of fact, they're much nicer, easier formulas. The mean is just n times p, and that's just your number of trials times the probability of success will give you your average, and it will always work that way. The variance is found by multiplying those two things together, also times the additional value, the probability value for the failures. So if you do n times the probability of success times the probability of the failures, you'll get the variance. And then if you just take the standard, to get the standard deviation, you just take the square root of that value. Matter of fact, you can just usually do this all at one time. We don't really want to know the variance most of the time, so we want to know the standard deviation. So Let's do a quick example of that, and we'll move on to Poisson real quick. So we just want to calculate the mean and standard deviation from that chronic bronchitis problem where we had n equals to 1500 and p equals to 0.05. Should be noted that we need q as well, but that's just 1 minus p. And again, I'm going to do this entirely in R instead of writing it down here on this slide. But I'm going to define those three variables in R to start with, and I can use them. So up here, I'm going to define the variable n to equal 1500. That's what it was from the slides. My probability of success P I'm going to define as 0.05. And Q I'm going to define as 1 minus P. Since I've already defined P, I can just use that now whenever I want to represent 0.05 until I change that value. So be careful if you rename or do P equals again and change that to something else. You don't have to do this the way I'm doing it. You can just use the values and pop them in like you would a calculator if you want. I'm just trying to be a little bit nerdy with the way that programmers would do these things. So to find the mean, we'll just call it M. It's just N times P. We get the mean out. We get 75 for the mean. The standard deviation, which I will call sigma, because that's the symbol for it, is going to be equal to the square root of N times P times the Q. Or you can actually enter those values in, but it's got to be taken. You got to take the square root of it for the standard deviation. And when I do that, I get that sig should probably be like 8 point something. And I'm typing in the commands afterwards to show what the output is. But you can usually see these things over here to have way more decimal places than you'll need over there. A word about the standard deviation real quick, a quick aside here. This is probably a good amount of decimal places to have a standard deviation rounded to. The more decimal places you have your standard deviation rounded to, the more accurate you're going to be when you have to use that value in other calculations. So be wary of that. Now, most of the functions we'll use in R will do this for us, but if you're ever having to do something where you have to calculate this before you plug it in, having more decimal places is always more accurate in your final calculations. Don't round things off early when you have to use them in other places. For publication purposes, it would be okay to round this off smaller. If you're writing a paper or something and you just wanted to round that to 8.441, that's acceptable, but like for calculation purposes, you don't want to do that. Okay, and that's pretty much it to that. So there's our mean, 75, and there's our standard deviation 1. Again, this stuff is also in the R code only text file in D2L. All right, so let's move on to talk about the Poisson distribution. It's one of my favorite ones to pronounce, Poisson. It's named after a mathematician, this particular distribution. But Poisson, the distribution here is used to express the probability of a given number of events occurring in a fixed interval of time and or space. So really it's just like you have a certain time interval or a spatial interval that you're looking into, and the variable of interest is how many times do you see an event occur in that time period or in that interval. So the events occur with a known average rate. This is usually something known over like a study that's been done over a specific time period originally. And this is what we call, which you'll see in the notation, and we call lambda. It's the original mean of something, the number of times we've seen an occurrence happen over a specific time period. This event also occurs with this known average rate and independently of time since the last event. So if you have a new period of time, then that period of time is independent of the previous one. So independent still falls into play here. It can also be used for the number of events in other specified intervals, such as so the space I was mentioning before would be things like distance, area, or volume. If you have an interval involved in that, and you want to know how many times a certain thing has occurred over this time, over this area or distance or volume, then you can do that as well with Poisson. So some examples of Poisson experiments would be like the number of emissions that are seen or observed in a 1 second in 1 second for a radioactive particle. The number of pinholes in a surgical glove. The number of deaths, and also the number of deaths caused by typhoid fever over a 1-year period. We're going to look at that specifically here in just a second. But notice that each one of these things has either the first one has a 1 second interval. So the number of observations seen in a 1 second interval. Number of pinholes in a surgical glove, that's more of an area problem, specifically surface area. You count the number of pinholes you find on a surgical glove. You might not want to do it across the whole glove, but that's neither here nor there. We don't need to get into that. The number of deaths caused by typhoid fever over a 1-year period. The 1-year period is our interval of time, and we want to see how many instances we see of this thing. All right. So it's Poisson. More specifically, Poisson random variables arise in scenarios, and this is kind of the properties, so to speak, or at least the first couple of bullets here are properties. Events are occurring in a specified interval of time. That's the first qualification for being Poisson. The variable of interest or our random variable is defined as the number of observed events during that specific time period of time. Okay, and those are really two of the mainstays. Those are really the two important things about Poisson. Another thing about Poisson is that it's really related to the binomial experiment that we looked at before. If we divide the interval into small equal subintervals, as many as we want, so we made them so small that only one event can occur or not occur during that subinterval, then we can actually treat it like the Poisson, like the binomial. As a matter of fact, Poisson kind of comes from the binomial distribution. Mathematically, that can be shown, but we're not going to worry about that here. But because of that, if you think about the binomial, each subinterval actually acts like our trials, and where we have the same probability of success. Either we observed the event in that little subinterval or we didn't. Also, the subintervals are independent of each other because either they're so small, only one thing could occur in those little subintervals, and so therefore, these two guys are really related. This is not something. This is really beyond the scope of this particular course. This is more for a 3600 class or with the prob stats class, our stats theory course. But nonetheless, it's good to know that they're related. Here's the formula for the Poisson probability distribution. The PDF specifically, the one that gives you the exact output, is this formula here. And I'm not going to really get too specifically into the formula because we're not going to use it by formula here, and I don't want anybody to use the formula here. But the part of the formula, the mu symbol here, which we usually is used to represent the population mean, is calculated a little bit differently. The lambda value, which is already known from the previous from a previous study or the original time period where data was originally collected, is lambda. That's usually going to be given to you in most of these problems anyway. And the time t is like, did you use the whole interval? T might be 1. Did you shorten the interval a little bit by saying let's go 3/4 of the time? Then you'll have to multiply that lambda times 3/4, or you have to basically the mean for a Poisson distribution is proportional to the amount of time you're interested in looking at. So you can lengthen that time or you can shorten that time. But this formula will help you get the right mean to use in the cases that you need to use it in. We'll see that in the example. The mean and variance are the same in this distribution, so there's no special formulas here. Once you know mu, you know the mean and the variance. To get the standard deviation, you only need to take the square root of the variance to get it. It's as simple as that. We're not going to really work with this much in this class, but it's just good to know. Now the functions in R are kind of similar. You'll notice that any PDF we use, will have a D at the beginning of it, just like you saw D binom for that. This is D plus. And for the cumulative one that adds together, you get P plus. And the same rules that we did there apply, except for the first, you only have 2 inputs here. And if you want to do the lower dot tail equals false, that can come into play for the P plus down here. Lower dot tail can be used to add up, and it works the same way as it did in the binomial one that we showed, so I won't go into that. But the y is your variable of interest, your discrete random variable y. That's where you want it to tell it to stop adding up to, or in the case of the lower dot tail, where you want it to tell it to start adding after. And mu is the value that we get up here in that mu equals lambda times t. All right, so let's kind of look at the graphs of what happens and how you can change the shape of the graph depending on the time interval. Because remember I said that the mean here is subject to being proportional to the time unit you're using. So if you use the entire time period that was originally used, where t equals 1, and you have your lambda of 4.6, then your mu stays 4.6. And in this particular instance of this example here, we get a left skewed distribution. If we change that time period to 3/4 or 75% of the original time period, then it changes our mean from 4.6 to 3.45, and our data starts to look a little more normal. And then if we change it to half the time, it gets a little more skewed to the right, and then it becomes severely right skewed if you change it to even smaller unit of time like 0.25. So decreasing that time period from the original time period of 1 shifts our graph in the direction from left skewed to normal to right skewed. Eventually, the smaller we get with that time value. If the time value were to jump, then we would imagine from this original one that this would become more what we call left skewed. All right, so just an observation to make. So let's do our last example here. Consider the distribution of the number of deaths attributed to typhoid fever over a long period of time of 1 year. All right. Suppose the number of deaths from typhoid fever over the 1 year period is Poisson. So we're telling you what the distribution is. It's Poisson distributed with a parameter of lambda equals 4.6. So we're using the same value we had in my graphs a minute ago. Calculate the following. We're going to do 4 different things. We're going to calculate the mean of the Poisson for 9-month and a 6-month period, and then we're going to use those values to calculate probabilities that we see at least 4 deaths in the 9-month period and at least 4 deaths in the 6-month period. And then we're going to do something a little different where we calculate the probability of finding at least 2 deaths and at most 5. So this is an interval here. This is that scenario I talked about way earlier in lecture where I said, this is like finding the probability of 2 less than or equal to the random variable y less than or equal to 5. What we want to do is add all the probabilities from 2 up to and including 5. And we'll do that here in just a minute. But we're going to do that in a 6-month period. So I'm going to do that on a blank page here. 1. Let's find the mean and the means for the 6-month and a 9-month period. Okay, so let's do that. So the mean for the 9-month period, I'm going to call it in R. I'm going to call it mu9. Let's just recall that mu equals lambda times t. So lambda in our problem is 4.6. And the time period's 9 months. This 4.6 was defined over a year. So in relationship to that year, 9 months is shorter. So we need to multiply this by 9 out of 12 to kind of fix that up. When we do that, we should get something like 3.45. And we'll do this in R in a minute to showcase that. If we do for mu6, for the 6-month period, I'm going to call it mu6 in R. But that's just going to be 4.6 times either 6 out of 12. So we'll give a factor of the time period being half the time. Or you can multiply it by 0.5. And this should give us roughly about 2.3. Okay. So those will be the values we'll get when we plug them into R. And then we'll work on number 2 in R as well. So let me clear this out. So if I plug in mu9, I get 4.6 times 9 over 12, and then mu 6 equals 4.6 times 6 over 12, or 0.5. And we look over there, and the mu 9 and mu 6 over here in our global environment show 2.3 for mu 6, as I said, and 3.45 for mu 9. So those are our means for those two particular time periods. Now we can use them. And number 2 asked us to find the probability of seeing at least 4 deaths in the 9-month period. So this is 9 months. So it's the probability that y is greater than or equal to 4, at least 4. And for us, I'm going to use the lower dot tail version. Remember, since we want to be greater than or equal to 4, we want to put the number into our p-binom function that is just smaller than 4, the next whole number down. So I'm going to put 3 in there. I'm going to put the and then I'm going to put the mean, because that comes next, which is in this case for the, I'm going to call, since we call it mu 9 in R, I'm just going to call it mu 9 here. That'll give us our 3.45, and I'm going to put lower dot tail equals false in there, and that should give us the answer we want. Matter of fact, I'm just going to copy and paste that in there, and let's see what we get. So that's a fairly big probability. The probability that we see 4 or more deaths in this case is going to be 0.452. That's about as close to being happening as not happening, so it's like right close to 50%. So 0.4525405 is what we get. You could have also done this real quick, 1 minus p-binom. Do the 1 minus situation where you just do 3 comma mu 9, and it should have given you this. Oh, sorry, not p-binom. P plus, and you get the same thing. All right, number 3, real quick. It's the same. Basically, it's the same thing. Don't need to rewrite this one out necessarily on the slides, but it's the same thing we just did. So if I bring back my original p plus with the lower dot tail equals false in it, the only thing I'm changing here, and I hit the up arrow key to get back to bring back that particular thing from earlier. If I put in mu 6, we get that it dropped down. The probability dropped down to 0.2. So the smaller the time period, the smaller our probability was that we see that event happen. We kind of expected that from the way we saw the graphs, though. Okay. The last problem. So this would be p-binom 3 mu 6 lower dot tail equals false, and we got somewhere around 0.200 2006529. The last one said, find me the probability that you see at least 2 deaths and at most 5 deaths. So we want to really add up those values together. There are more than one way to do this particular problem as well. But if you think about the numbers that we have, we're going to have 0, 1, 2, 3, 4, 5. If you think about the number line of discrete random variables, that is, we're going to have 0, 5s, and this can keep going up, ... for a long period of time because there's no stopping point with Poisson. But we want to know, really, we want to add up the numbers between 2 and 5. We don't care about these numbers above. These numbers below aren't helpful to us other than the fact of this 1 here is going to become important. What we want to do, use a different color, we want to add all from 0 through 5 together to add the total there, and then we want to take away the 0 and the 1. So in R, how we do that is we start out with the big area first. So P-POISS, and I keep writing binom up here. Let me correct that real quick. Hopefully y'all caught me doing that. I caught myself doing it. So we're going to take P-POISS of 5, this is the 6-month period we were dealing with this in, so mu6. And we're going to subtract from it P-POISS of the area I don't want in there. I want to continue 2 through 5, so I'm going to put 0. I want 0 and 1 added together, so I'm just going to put a 1 here and mu6, and that will give us the answer we want. So let's plug that into R real quick and see what we get. P-POISS 5, mu6 minus P-POISS 1, mu6, and throw that in there and hit enter. And I get 0.6391701. So there's a lot of probability between 2 deaths to 5 deaths. Okay. The one alternative way, and we'll be done, that you could have gotten this, you could use the sum command to help you here, and the dPOISS function instead. Inside the dPOISS function, you don't have to just enter one number in there. You can enter a series of numbers. So this is a quick way to do this as well. You could put 2:5 and say, hey, I want you to take find me the probabilities for 2 through 5 when my mean is from a 6-month period, and I want you to sum those things together. So the dPOISS function inside here will get us the probabilities. The sum function will take those probabilities and add them together for us, and we should get the same thing. So this isn't also, when you're doing intervals, this is probably even a better way to do it. And again, I have these additional notes here in the R code only file, so you have access to those as well. Please, if you have any questions about this stuff, don't hesitate to reach out. We'll have the Thursday night Q&As, so if you want to go over some more things kind of like this, we can do that then to kind of get it clarified for you. Or you can stop by my office hours. Hope everybody's doing great, and I'll talk to you later.